In the last video, I said that we would look at more detail of how you find the inverse of a given function, assuming that function is invertible. And in the last video, we looked at specifically this function, f of x equals the cube root of the quantity 2x plus 4, that minus 7. So found the inverse by really just decomposing this into 4 individual functions. If you start with the perspective, if you start with x, 2 times x would be the first function, adding 4 the second function, cubing's the third function, and minus 7's the last function. The inverse will invert each of those functions in the opposite order. So we have to start at the end, minus 7, well, adding 7's the inverse of that. That takes us to the cube root. The cube root function is invertible. Its inverse is the cubing function. That would give us 2x plus 4. If you subtract 4, we undo the adding of 4, and then at the end we divide the whole thing by 2. So remember that the idea here is that x is an input and y is an output, and f of x and y mean exactly the same thing. And so you can think of the function as starting at x and taking x to y. So for example, if x is 12, we have f times 12 is equal to the cube root of the quantity 2 times 12 plus 4, that minus 7. 2 times 12 is 24, plus 4 is 28. Cube root of that, we don't know exactly what it is. It's an irrational number, as if you were to take all the numbers from 1 to 100 and take their cube roots, hardly by numbers I mean integers, 1, 2, 3, 4, 5, 6, so on. Well, there aren't many of them that have rational cube roots. 1, cube root of 1 is 1, cube root of 8 is 2, cube root of 27 is 3, cube root of 64 is 4, and I think that's it. So all the other numbers from 1 to 100 would have irrational cube roots. But we can say that the cube root of 28 should be pretty close to 3, because the cube root of 27 is 3, and 3 minus 7 is negative 4. And so the number I've got here, negative 3.96, which I got with the calculator, is a reasonable approximation based on what we could do without a calculator. And of course, we live in this wonderful age where we don't have to worry about how to do things without a calculator, at least not right now. Now, if y is an invertible function, then it follows that x would be a function of y. I'm going to talk about this in a slightly more elevated level of reasoning than we usually apply in college algebra. In college algebra, functions are fairly new to people, and we just like to think that we're always going from x to y. Sometimes might change the input to some other letter just for fun, and the output could be changed to something else, but it's almost always x and y. And then for graphing purposes, that lines up nicely. But there's a higher level of thinking about this where you can say that, well, if x is a completely generic input and y is the completely generic output that goes along with it, then if the function takes x to y, then logically the inverse function would take y to x, which is what I've written here. X equals the f inverse of y. Now again, that's not typically the way that this is presented in college algebra. And I'm not going to dwell on the point too much, but I do think it's worth thinking about a little bit. So what we have here is y is this function of x that we looked at before. And so from this perspective, if x is the inverse function of y, what we could do is just say, well, this function has y solved for in terms of the input x. You input something at x, you end up with something at y. It's handy for calculation purposes, such as what we have here. where I calculated f of 12. Well, suppose we got this number almost -4, and you put -4 in for y. How would you go about finding the x value that corresponds to it? Well, the answer to that question is really how we can find the inverse function. So if I wanted to take this equation, y equals the cube root of the quantity 2x plus 4, that minus 7, and solve that for x in terms of y, instead of the way it's given originally as y in terms of x, well, we just undo those 4 simple operations that I was talking about earlier. Start by adding 7, then cube both sides of the equation to eliminate the cube root. So now we have the cube of the quantity y plus 7 is 2x plus 4. Well, we can undo the addition of 4 by subtracting 4. And then that gives us 2x, and then to finish solving this for x, so that we have x in terms of y, which is what the inverse function is, well, I'll just divide the whole thing by 2. Instead of showing as division, I'm show it as multiplication by 1/2, same thing as dividing by 2. 1/2 times the quantity y plus 7 cubed minus 2 is equal to x. So the inverse function as a function of y would be x equals f inverse of y, which is 1/2 times the, I have to change that, there's a, and change it here also. It's an error from some previous work that I hadn't fixed yet. Okay, so anyway, we've got x as a function of y, the inverse function of y. The f inverse is just representing the fact that we had a previous function that was we were calling f, and the inverse function relates this to that f. Well, this is logically correct, true, reasonable, and all that good stuff. However, we're going to do something which is not logically true, reasonable, and correct, but is the convention that is used in college algebra anyway, where we're going to go ahead and say, okay, we want all of our functions to go from x to y, and so we're just switching the roles of x and y around. So wherever you see a y, you write an x, and vice versa. So now we're back to y equals f inverse of x equals 1/2 the cube of x plus 7 minus 2. Now that convention is the reason that if you look at a function for invertibility by checking with the horizontal line test, well, if you switch the roles of x and y around on that graph, then that means that horizontal lines become vertical lines, and so the horizontal line test is kind of looking at the inverse function from the perspective of the vertical line test to see if it is indeed a function. And likewise, if you look at the 2 graphs, they're going to be reflections of, by 2 graphs I mean the graph of the original function f and the new function f inverse. If they were both plotted on the same xy coordinate system, using the perspective that both of these are mappings from x to y, well, they're going to have a symmetry about the line where x equals y, and that's a line that makes a 45-degree angle with the positive x-axis and positive y-axis, and negative x-axis and negative y-axis. And you should have run across that in your reading. If not, go back and look at the pictures some more. Okay, so anyway, the main point is all of our functions are from x to y as a matter of convention, but at the higher level of mathematics, they will often get rid of that and trust the student to try to figure out from the context what's going on. Now this process I just went through, you can really apply that to lots of functions where you, so if the original function has y in terms of x, you solve it for x in terms of y. But there are sometimes some complications with that. So here we have a new function g. G of x is a rational function. It's actually the ratio of 2 linear functions. 2x minus 18 thought of by itself would be a a linear polynomial. Same thing with 5 minus 4x. We'll look at the graphs of these in some detail later on, and some other properties of rational functions. But it turns out that some rational functions are invertible. Those which are ratios of linear functions like we have here are invertible. And then how do you find the inverse? It's a little bit trickier than what we were just looking at, because we have two different starting points, two different x's here. So how do you solve for x when x shows up in two different places? Now, I think I'll actually just get rid of this. I was going to talk about that, but I don't think it's going to add much to our conversation, so I'll get rid of that. Box was just there. How to find the inverse function of y equals. So I was calling it g. It seems to have disappeared. I got rid of more stuff than I wanted to. Let's see. To bring back, there we go. Okay. Okay, so there's my function. Okay. I know what happened. I just scrolled up too far. Okay, so originally I'm calling the function here g, and I'm going to get rid of that for the time being, but I'll come back and talk about the function as g later on. How do you find the inverse of this function? So if I just call it y, so we don't have to mess with the function notation, at least for now. Well, we have a fraction here. Whenever you're solving an equation involving a fraction, one thing you want to consider is maybe make that fraction no longer a fraction, right? An equivalent expression, equivalent equation that does not have the fraction in it. Can do that by multiplying by the denominator here, 5x minus, it's going to be 5 minus 4x. If we multiply through by that on both sides, it'll cancel on the right side, so the 5 minus 4x doesn't show up on the right anymore. And then we have it times the y on the left. At that stage, we don't really have much choice than we either go back to a fraction again, which we don't want, or we distribute the multiplication of y times 5 minus 4x. So frequently in mathematics, if you're not sure what to do, just consider your possibilities. You probably only have one or two possibilities. Choose one of them and see what happens. So if we multiply it out, we get y times 5 minus 4x, 5y minus 4xy. We're trying to solve this for x, and so we will go ahead and manipulate it so the x terms are all together and the non-x terms are all together on the other side of the equation. There's a couple ways of doing this. I chose the one that gave me no negative signs. So added 4xy to both sides, added 18 to both sides. So I got 5y plus 18 equals the expression 2x plus 4xy. There's not much I can do here. I can't add 2x plus 4xy. So really just by process of the only thing I can think of is factor out an x. If we factor out x, we have x times the 2 plus 4y quantity. And now, you'll notice we only have the single x showing here. It's x times two terms, which is why we had two x's previously, and now we only have one x. And here you can solve this for x by just dividing through by the 2 plus 4y. So that would give us x, and that x is the inverse function as a function of y. Now, at a higher level of mathematics, I would just leave it like that, but as I've been discussing here, in this particular level of mathematics at college algebra, the convention is that our functions are from x to y, so keeping that in mind, we're going to replace these y's with x and this x with y and rewrite it like this. Well, let's see, I haven't done that yet. Oh, here. Yeah, here's the thing I was just talking about all over again. And then we write it like this: y equals g inverse of x equals 5x plus 18 over 2 plus 4x. Now you look at that and you say, well, something strange about that, that it can't be both of those things, and you're absolutely right. It can't be both of those things. It isn't both of those things, except in the sense that the input is irrelevant and what you call it, and the output is irrelevant what you call it. We wouldn't want to call both of them X. That would be really confusing. But whether the input's X and the output's Y, or the other way around, I'm sure you get the idea by now. So I'll quit belaboring that particular little detail. Okay, so if we take that, so here actually I'm starting with, so what I'm going to do with that is I'm going to not really go through all of the algebra checking that this is actually the inverse. You could do a quick check by plugging in, let's say, if X is 0 here, what do you get for Y? Well, if X is 0, 5X is 0, 4X is 0, we just have 18 over 2, which is 9. So 0 goes to 9, which means that in the original function, which we have here, 9 would have to go to 0. Well, if you plug in 9 here, 2 times 9, 18 minus 18 is 0. 0 divided by, I guess, 5, which should still be 0. Now, that doesn't prove that this function and that function are inverse of one another, but it is suggestive that they could be. At least it doesn't rule out that possibility. To really check, as I mentioned in the last video, you would actually have to calculate G inverse of G of X and G of G inverse of X, and check that both of those compositions take you to the identity function X. And they will. But another thing you can use to check, which is also part of the definition of inverse, if two functions are inverse, so going back to G, which was this thing right here, and actually throw in the G again to remind us of that. Get so many functions floating around up here, I can forget which one's which. So one of the problems with just calling the output Y is, well, if you have two different functions and Y is the output in both cases, that doesn't always work for us. So another value of the function notation, calling it G, and getting away from the Y. The domain of G, if you look at this function, the domain is everything except for 5/4. The reason we can't have 5/4 in the domain, so that's what this says, the set of all X such that X is not equal to 5/4. This is set builder notation for the domain of G. Well, if X were 5/4, if you plug that in, we'd have 4 times 5/4. The 4s would cancel and end up with a 5. The denominator would be 5 minus 5. 5 minus 5 is 0. Can't divide by 0, so that's not a possibility. So 5/4 is not in the domain, and you'll just have to take my word for it that everything else is in the domain, all real numbers other than that. I sort of implied in my notation here that X is a real number. Sometimes that's actually stated explicitly if there's some question of it. But for us, our functions are always functions that are from the real numbers to usually the real numbers. So we don't need to worry about what's that we're using. So we just have to note that we're leaving that one number out. Okay, so anyway, if this is the domain, it turns out the range of the inverse function is going to be the same. Because the inverse function has to take, so to speak, Y to X. And that means that, that nothing's going to be set to 5/4 because 5/4 was not in the domain of the original G. Now, again, this would actually be clearer if I were using a notation which said that X is here, but because ranges typically are thought of as being outputs, which are thought of as being Y's, I used the Y symbol to represent that. So it doesn't look like it's necessarily the same set, but these two sets are actually the same set. The X, the Y, that's just a generic element. And so the set of all X such that X is not equal to 5/4 is the same as the set of all Y such that Y is not equal to 5/4. There's no difference between those sets. Okay, so I'm going to show that the range of G inverse does not contain 5/4 by trying to solve this equation. 5/4 equals G inverse of X. So if this were in the range, there would be some X that would be sent to 5/4. And I'm going to show that there is no X that's sent to 5/4 by trying to solve this equation. 5/4 equals 5X plus 18 over 2 plus 4X. Remember, this was the inverse function that we have back up here, 5X plus 18 over 2 plus 4X. That was solved for back here. Okay, so doing the algebra here, make sure I copied everything correctly. Well, this is a proportion, one fraction equals another. And you can cross multiply, take 5 times the quantity 2x plus 2 plus 4x rather, 5 times 2 plus 4x, and set that equal to the product of 4 and 5x plus 18. This is called cross multiplying. It's a way of solving a proportion by eliminating the fractions. It's really just based on clearing the fractions. If you multiply both sides of the equation by 4 and 2 plus 4x, you'd end up with this equation here. Okay, simplifying by removing the parentheses, we get 5 times 2, 4, looks good, 4 times 5, 20, okay, 4 times 18, okay. Notice we have 20x on both sides of the equation because here we had 5 times 4x and here we have 4 times 5x. Okay, so if we subtract the 20x from both sides, well, it looks like the solution set to this equation is the set of all x's for which 10 is equal to 72. And of course, 10 is not equal to 72 no matter what x is. So there's something wrong here. It's not obvious when you first write down this equation that it can't be true. But as we attempt to solve it, what we find out is that this equation has no solution to it. In other words, 5/4 is not in the range of the expression 5x plus 18 over 2 plus 4x. 5/4 is not in the range of the inverse function that we just found. So sure enough, the domain and the range of G and G inverse line up as they're supposed to. We could also check and see, I'll leave it to you to maybe check this on your own, that if you were to look at the domain of G inverse, which is pretty simple, everything except for -1/2. If we plug in -1/2, we'd have 4 times -1/2, which is, of course, -2. -2 added to 2 would be 0, and we'd be dividing by 0. So the domain of G inverse is everything except for -1/2, which means that the range of G likewise has to leave out -1/2. So you could set up an equation 2x minus 18 over 5 minus 4x is equal to -1/2. Try to solve that. You'll find that it does not work. Okay, as with all mathematical topics, there is much more that could be said here. And maybe it'll be covered in a subsequent video lecture. If you have a particular question, I'm willing to take requests and look at a specific issue. But you can't learn all of this at once, so just learn what you can as you can, and over time you'll build up a larger and larger repertoire of mathematical knowledge that you can apply to different things. So that's it until the next video.